Hello class, this is CSE 5250, section 61, week 7, though really it should be week 6, fall 2024. I wish I'd gotten this out sooner than I did, but I wanted to make sure that everything is absolutely correct and is not error prone. So to that end, I ended up revamping all the material for chapter 4 of the textbook. So this is the newly created set of slides for chapter 4, part 1. So a lot of this is going to be review from the review slides from operating systems. This is going to be a rehash of that. So of course, hopefully we know what a process is by now. If you've ever taken CSE-4600, you are expected to know what a process is versus what a thread is. So a process is just an instance of a running program. It has memory allocated to it. It has other resources allocated to it as well. It's going to have some information about the state of the program itself. It's going to have several things in memory as well. The executable code. The memory also includes the stack. It also includes the heap. On most systems, by default, a process's memory is private, so no process can access another process's memory except for shared memory setups. So what we're trying to do here is we want to have, ultimately our goal here is to have a multi-threaded program, but we have to talk about what a thread is first. So we have multiple processes and we want them to cooperate with one another to complete a task together. The problem is, those processes have separate memory, unless we have shared memory between them. We can set up parts of each process's memory spaces so that they are shared between processes. And that is one way we can get processes to work together on a common goal. However, that is a little bit clunky. We want something that's a little bit simpler to set up. So, what if we have a process that creates another process, but that process shares all the memory that the original process had? That's a lightweight process. And by that, instead of those two processes having separate memory spaces, they all share 100% of all that memory space. This is called a lightweight process, but it goes by a more common name, thread. So a thread, think of a thread as a thread of execution. It's going to be some sequence of steps that a program has taken to do some work. When we have a multi-threaded program, basically what's happening is there are multiple threads of execution. They all diverged at some point from the main thread to do something else. When they diverged, what happens is, now the computer is seeing multiple processes. Well, it might be seeing these threads as different processes, but each process is going to do something that is related to the work being done. So a shared memory program is one process, but with multiple threads. And shared memory in that these lightweight processes, or rather threads, one program. It's one program, and all those threads are sharing the same memory. It's not different instances. It's not copies of the same program, but it really is the same program. So, if you are to run a piece of software, it's going to be loaded up as a process. If you loaded up that program again, now you have two instances of the same program. That isn't multi-threading because it isn't it's not multi-threading because it's two separate instances of the same program. But it becomes multi-threading if one program creates multiple threads, and those threads share all the same memory, and they're all working together to accomplish some task. So, we're going to begin with a whole nother Hello World program. So this one's a little bit different from the one that you were working on last week. This one is set up so we do one thing different. Instead of changing the thread count and recompiling the program every time you want to run the program with a different number of threads, when we run this program, we pass in a command line argument specifying the number of threads that we want to run the program with. Compiling the program, okay, so eventually you will be writing this Hello World program, even though you just did that already, but you're going to be using this as a base to write your next program. You got that? We're going to be writing this again, but we're going to be using it as a base to write our next program. To compile this program, we can just use the same command from the previous lab instructions, but we're going to add a few more arguments to that. Among which is wall. This is short for warn all. This enables warning messages that help you with writing cleaner code. It's optional, but it's highly advised to include wall here. When we run this program, we run it with some number of threads. So we do /file name, and then we pass in the number of threads that we want. So we say, for example, I want to run this program with 10 threads, /file name 10. And as per usual, the output's going to be out of order. This is normal. This is something that's going to depend on how your operating system's CPU scheduler works. So it might decide to run the first thread first, the second thread second, but it might go out of order at some point after that. This is what's called non-deterministic. This is a non-deterministic ordering. We can't really predict how it's going to work. Let's look at the preliminaries. Of course, we're going to need the pthreads library. That's line 3. So in # include pthread.h. We're going to need a global variable. This is going to be accessed by every thread. So int thread count, but it's not initialized to anything. Not yet, at least. Okay, so int main. Probably up until now, you only had int main, left parenthesis, right parenthesis. This could be the very first time that you're seeing, or maybe the first time in a while, that you're seeing int main with stuff inside. So, int argc, character star, argv, and then square brackets. This is basically a setup for having the main program, the main function, accept command line arguments. So when we run a program, we're going to pass in a quantity of threads. So this is how we take that value and tell the program, run 10 threads. We're going to take argv. Argv is an array of text strings that we are going to parse as command line arguments. So argv is an array that contains everything from // as an array. So file name is going to be included. The 10 here is going to be included. We don't want argv0 because that's just the name of the program. We want argv1 because that is the string that we want to parse as an integer so that we tell the program to run with 10 threads. When we call strtoll. We need to pass in 3 arguments. The first one is the string that we want to parse as a number. The second argument is end p. Just pass in null for that. And the third argument is base. We're going to be parsing these values as base 10 numbers, so just pass in 10 for that. So, go back here. strtoll argv1 null 10. That says parse the first thing. Well, technically it's the second thing, but it's ordered from 0. So, parse not the 0th thing, but the first thing in that array of command line arguments. Parse argv1 as a base 10 number, and then assign thread count to that number. So when we pass in 10 as a string, it's going to be a string first. Technically it's going to be a character array, but I'm going to call it a string. We take that string, parse it as a integer value, assign thread count to that value. Now the program is going to run 10 threads. Okay, so pthread t, that is our thread handles. Or rather, it's a pointer to thread handles, because the program doesn't know ahead of time how many threads it's going to run. So we have pthread t thread handles, but sometime after that, we need to allocate memory to that. So this is done on line 20 over here. I did not highlight it when I should have, but maybe I'll have to do that as a corrective measure. So thread handles equals malloc, and then we pass in thread count times size of pthread t. So this is going to allocate memory for all of our thread handles, and we have as many thread handles as there are threads. So thread handles equals malloc thread count times size of pthread t. And this is dynamic memory allocation. So that means at the end of the program, when we're done with this block of allocated memory, we're going to deallocate that. That's all the way at line 36. So that's free thread handles. That's gonna deallocate all the memory that we allocated for our thread handles. But before we get to that, we're gonna use these thread handles for our threads. So we allocate our memory for all of our thread handles, and then we call pthread create. We're gonna call pthread create for every thread that we have using a for loop. So if you go back up here, back on line 13, that is a 64-bit integer for a variable called thread. That is for the for loop over here. So for thread 0, for thread equals 0, thread is less than thread count, thread plus plus, we're gonna call pthread create. We're gonna pass in the address to one of our thread handles. We're also gonna pass in a few more things after that. So pthread create creates a new thread, and it requires 4 arguments. The first one is pthread t star. That is a pointer to the thread handle. Of course, we need to allocate this before we call pthread create. Attribute p, just ignore that for now. We're just gonna pass a null for that. That's the second argument. The third argument is start routine. That is the name of the function that the thread is going to run. And args p. These are function arguments for the function that's going to run. So look at the function prototype for our hello world function over here. That's all the way on line 9. It has data type void star for its return type, but its command line, not command line, but its function arguments are also of type void star. Why is that? Because we are this thread value here. We're gonna use that for the thread's identifying value. The textbook calls it rank. So every thread is going to have a unique rank. But for this function to be able to use that, we have to cast it to void star, so that way, when it's passed into the hello function, it's going to be of the correct data type. So we pass in the thread's rank, cast it to void star. let's talk about that void star, by the way. The thread and void arguments are of type void star. And this type can be cast to any pointer in C. For the void argument, this allows us to pass in multiple values into a thread function as a list of values. Similarly, the return type of void star allows the function to return multiple values. So we might return a list of values that we might use as part of putting together our final result. For this hello world function, we only need to pass in one thing, and that is the rank. There is nothing that we're going to be returning, so we don't have any return values here. So, after all the threads are created, the main thread's simply gonna say hello world. After that, or maybe while that's happening, every thread is going to do work. And that work is described using and that work is going to be calling the hello function down here. Once that's done, we need to call pthread join and pass in that corresponding thread's thread handle. We're going to call pthread join in a for loop. That way it calls pthread join for every thread by passing in that thread's corresponding thread handle. pthread t is going to be the first argument for pthread join. This is the thread handle of that thread, but it's not a pointer to that thread handle. And the return value p, that is for receiving any return values from the thread. We're not going to be working with that. So we don't have any return values from this function. So that's why the second argument for that one is null. If we have return values, we can catch them in some variable and then cast them to the right data type. We don't have to deal with any of that right now. The act of a main thread creating multiple threads and waiting for them to finish, that's basically the fork and join model. Calling pthread frees up any resources associated with that thread. If we forget to do this, then we might get zombie threads. That is where we have, it's kind of like a memory leak. So you allocate memory and then you forget to deallocate it. That's called a memory leak. We allocate resources to a thread, but if we forget to deallocate those resources, we get a zombie thread. They are basically resources that are locked up in a way that we can't use them anymore until we restart the system. This might prevent us from creating new threads if we leave this unchecked. If we want the main thread to not wait for a thread to finish, then what we would call instead is pthread detach. That way, once that thread terminates with the rest of the program, any resources associated with that thread is still deallocated properly. Also, it's worth mentioning that every one of these pthread functions returns an error code that we can use for debugging purposes. We're not going to do any of that, but it is good practice to use those values for checking whether these functions operated correctly. So it's a good idea to, even though we're not doing anything with the return values of all of these pthread functions, it's probably a good idea to, do that. Now, before I begin with the next section in the book, I have the program here. So this is in my Linux virtual machine. It is the Hello World program that is described in the textbook, that is described in the PowerPoint slides. So up here we have our graphical weirdness here. Ignore that. So we have our include directives here for standard.io.h, standard library.h, and of course, pthread.h. We have a global variable here, and then we have our hello world function here. Return type void star, and rank is the, as I said, the rank is the, think of the rank as the thread ID for each thread. Not the system assigned thread ID, but a different thread ID that is of convenience to the programmer. So void star is going to be the data type of rank. We're gonna be casting that to an integer value later on. When we run this program for the first time, when we run this program, it's going to take in some command line arguments that's going to be stored in this argv here. So this is an array of strings, even though it's not really strings in the data structure sort of sense. I'm just calling it string because, well, I guess I'm overloading my words here. Anyway, it's going to be an array of strings that we're going to be using to figure out how many threads we want to run. We have this long thread here. That's just a 64-bit integer that we're going to be using for our for loops later on. And of course, we have our thread handles over here, pthread, t-star thread handles. Before we do anything with thread handles, we first need to figure out how many threads are we running. So we do that using strtoll. We pass in argv1, null, and 10. That way, we can get our thread count and assign it to our global variable here. Well, the global variable was created all the way up here, but now we're assigning it a value down here. Once we have that information, we can multiply it with the size of pthread t. We pass that whole statement into the malloc function. That way, the system will allocate memory to our thread handles. And now we have all the thread handles that we need. Now we create all our threads. For thread equals 0, thread less than thread count, thread plus plus. We're going to call pthread create. We're going to pass in the address of one of our thread handles. So ampersand thread handles and then square brackets thread. That's our first argument. The second argument is null. We're not really going to work with that right now. The third argument is going to be the hello function here. And the fourth argument is going to be thread. This is going to be the rank that the threads are going to use to say hello world from thread number something out of something. However, that must be casted to void star. So when we call pthread create, it's going to be passed in not only the function itself, but any arguments specified here. So once those threads are running, the main thread is going to say hello world from the main thread. Once all those threads have done their work, the main thread is going to call pthread join for each of these threads. So it's going to call pthread join. It's going to pass, we're going to pass in a thread handle, and then we're going to pass a null because we don't have any return values from these functions. Once we're done, we're going to deallocate memory that we used for our thread handles. Because we're working with dynamically allocated memory, we allocate memory. At the end, we deallocate memory so that we don't have a memory leak. And then we return 0. And here's our thread function itself. So void star hello, void star rank. Okay, void star hello. Void star is the data type of the hello world function, but it's also the data type of the rank here. We're going to cast that back to a long. That is a 64-bit integer in Unix systems. It goes by a different name in Windows systems, and because of that mismatch, I would not advise doing this lab in Windows. I mean, you can, and there are instructions for that. It's just that because of all this mismatching, I would advise doing a Unix system, doing this on a Unix system, unless you know what to do on a Windows system. Anyway, we get our rank from having it passed into the hello world function. We cast that back to a long, and then we're gonna print out hello world from thread %ld of %d. We're gonna pass in that thread's rank and then the thread count. And remember, the thread count was a global variable that every thread was accessing. So that thread's going to say hello world from thread something out of something, and then it's gonna return. Okay, you wanna see this thing in action? Okay, I'm gonna close that for now, and then I'm gonna open in terminal. So I had already programmed, I I had already compiled this program already. So if you want to see how it looks to compile this program, I want to see if I can zoom in on this. Hopefully this is large enough to see on YouTube, by the way. That command is gcc-g wall-o. The file name is hello world. And then the source code file is hello world.c -lp thread. Okay, that means there was an error in the thing here. That should have been -wall. Okay, so I have to correct that slide. Yeah, I'm gonna have to correct that slide in a bit. Okay, so that is the command to compile the program. If we want to run the program, we do // hello world, press enter, and we get a segfault because we forgot to pass in the number of threads that we wanted to run. So let's try this again. /hello world, we're gonna run it with, say, 10 threads. And there we go. Hello world from threads 0 of 10, 2 of 10, 3 of 10, 1 of 10, 5 of 10, hello world from the main thread, 6 of 10, 9 of 10. So it works. And we can do this again with any number of threads. So I'm gonna do it with 100 threads. Hello world from thread 97, 99, 98, 66, 64. And remember, the order is hard to predict. Okay, so now we have a hello world program where we can specify the number of threads without having to recompile the program every time. So let me update this slide, and when this video is live, the update should also be included as well. So this is the command. It should be -wall, not wall by itself. Let's look at our next section. This requires quite a bit of setup though. So, I'm skipping the section on matrix multiplication, though I will be referring to it in here. So, consider an array of values in which each element is being accessed by a separate thread. Such is the case with matrix vector multiplication. So we are doing a linear algebra operation in which we are taking some vector and modifying its values by multiplying it with a matrix. Basically what happens is we are calculating a new value for each value in that vector based on the dot product between that and the matrix we're multiplying it with. So, as I mentioned previously, matrix multiplication is basically a whole bunch of dot products. If we think of a vector as the degenerate case of a matrix, then it's basically matrix multiplication all over again. But my point is this. We are calculating each value in this vector, and for each entry, it's being done by a separate thread. I guess an even easier example would be vector addition. So we're adding two vectors together, but the individual values in the resulting vector, that is done by a separate thread. So we might have some array that is like 10 entries long. So we would add vector, okay, so we could add, for example, A3 plus B3. And then that would be the value for C3. So C3 equals A3 plus B3. But the point is, in the general case, it would be AI. It would be CI, where I is some thread ID. it would be CI equals AI plus BI. And that is being done for each thread. That is being done for each entry by a separate thread. Basically, regardless of the operation, each element in the resulting vector is being calculated by a separate thread. In other words, each element is accessed by one unique thread. No element is accessed by more than one thread. So, we're looking at what happens when this is not the case. What if there is some variable that needs more than one, that has more than one thread that needs to access and or modify it? So, we're gonna look at this thing that calculates the value of pi. Consider the example of this. So this is a way of calculating the number pi. We are taking 1, subtracting 1/3, adding 1/5, subtracting 1/7, and so on and so forth. So that way we could describe the nth term as being -1 to the nth power times 1 over 2n plus 1. And if we want to get the exact value of pi, it would have to be 4 times this infinite sum. But we can get a good enough approximation if we, for example, considered adding up the first, say, 10,000 terms in this infinite sum. So that's the program that we're going to do next. The code shown below here, this is how it would be done if it was a single-threaded operation. So we would have a factor, and then we would have a sum. And then we would have a for loop in which we are incrementing sum by factor over 2 times I plus 1. Also, every time we do this operation, not only are we incrementing I by 1, we are also changing factor. We're multiplying factor by -1, basically. So factor equals negative factor. We are negating factor so that because in the sum, we are alternating between addition and subtraction. And then the result of that sum, if we multiply that by 4, we get pi. If we want to turn this into a parallel operation, given n terms and p threads, each thread should be given n over p terms to compute. And to store the total, we can make the sum here a shared variable. Each time a thread calculates a term, its value is added to the sum. So, before we even do that, let's do this on the spot. I'm gonna write out a program in which we are calculating the number of pi, the value of pi. So I'm gonna do vi pi.c, and that opens up vi, but I don't want to use vi, so I'm gonna press escape, type in :wq, that saves the file. So now I have the file called pi.c. There's nothing in here right now, but I'm gonna type in a few things. So, I'll just steal some boilerplate code from one of the other programs. So, include standard.io.h, include standard.library.h, int main, and you can write this in C++, by the way. You can write this in C++, it'll still work. I'm just going with C because that's what the textbook has us do. So, int main. I don't have any command line arguments except for how many terms I want. So I'm gonna steal some more boilerplate code here. So int main int argc character star argv. And then I'm gonna have a global variable for a number of terms. And once again, I'm going to steal some boilerplate code from here, get number of threads from command line, but we're not dealing with a multi-thread program right now. Rather, we're dealing with... Okay, So this is the number of terms from our command line. What I'm doing is writing out the hello world program, not the hello world program, the pi estimation program, as a single threaded program. And then I can use this slide as a reference. So let me just put this on the side monitor so I can type out this. Let me do this. For int I equals 0, I is just the number of terms, I plus and then factor equals negative factor. And then sum plus equals factor divided by 2 times I plus 1. And then I'm going to say print f pi is estimated to be %f period dot slash n %f dot backslash n, and then I'm gonna type in here 4 times sum. I guess instead of doing that, I could just say equals. I could just say sum times equals 4, and then I don't need this times 4 in there. So that's going to be the end of the program here. I don't think there is no memory allocation in here, so I can just say return 0. So this is going to be our base single-threaded program. We're going to do a step-by-step process of turning this single-threaded program into a multi-threaded program. And I would like that to be your next assignment. I did not give out instructions for that just yet, by the way. So let's see if this works. I'm doing this on the spot, and yeah, I'm doing it live right now. Alright, so I'm gonna do this. GCC-O pi.c. Will that work? Yes, it will. If I do /pi, I get a seg fault because they never specified how the number of threads I want to run with. And then now I'm getting more graphical weirdness here. So if I do that again, /pi and say 100 terms, I get pi is estimated to be 3.131593. That's not quite right. It's supposed to be 3.14159. So let's do more terms. Say that much. 1414193. No, let's increase the number of terms again. 3.14159. It should be a 2 after that, but I guess it rounded up. Because it's 26535 after that. So maybe we can get it to be even better if we add even more terms. Okay, I guess that's as good as it's gonna get. So now we have our single-threaded pi estimation program. So the idea is, we're gonna turn that single-threaded program into a multi-threaded program. We're gonna need to do a few things to that program, however. And it is this. Let's go back to our current slide. So now we have our multi-threaded. So we have a single-threaded program that we want to turn into a multi-threaded program. If we want to do this operation as a parallel operation, given n terms and p threads, we need to give each thread n over p terms to compute. Yeah, we could have it so that we assign each term to a separate thread. But now we have to work with a lot of threads. So an alternative to that is to divide the work between some number of threads. Okay, so we're going to convert our single-threaded program into a multi-threaded program. To store the total, we need to turn our sum into a global variable that each thread is going to have access to. Every time each thread calculates a new term, it's going to add that term to the global variable of sum. So we might have our multi-threaded function, multi-threaded code, have a function that looks like this. To divide the work between multiple threads, basically we need to write our for loop in a different way. So this is the single-threaded for loop. For I equals 0, I less than n, I plus plus factor equals negative factor. Check this out. It's not that, but rather for I equals my first I less than my last I plus plus factor equals negative factor. What's happening is this. We are dividing up this. Have you ever thought about unfolding an entire for loop so it's like the same for loops? Have you ever thought about unfolding a for loop? Well, maybe it's better to think about it like this. Consider a super duper simple example in which we have a 16 element array and 4 threads. So we're doing work on all 16 elements, but it's being divided between 4 threads in the following way. So the first thread does work on elements 0, 1, 2, 3. So it starts at 0 and stops right before 4. Thread 1 does work on elements 4, 5, 6, 7. Thread 2 does work on elements 8, 9, 10, 11. And thread 3 does work on elements 12, 13, 14, and 15. And we can generalize this to any number of threads with any number of elements, assuming that the number of threads we're working with, that perfectly divides the number with the number of for loop iterations we have perfectly without remainder. There is another way that we can do this, but we're gonna go with this for now. So what's going on in here is this. First, we need that long line I. That's gonna be for the for loop here. First, basically, each thread needs to calculate where to start, and where to stop. That's what all this is being for. My n is going to be my n. We are gonna use that to calculate my first I and my last I. So my n is going to be n, where n is the number of terms, divided by the thread count, where presumably n and thread count are both global variables. So my n equals n divided by thread count. And we use that to calculate my first I and my last I. That is what these values here are. So we start at and stop before. This is my first I and this is my last I, basically. So my first I equals my n times my rank. My last I is going to be my first I plus my n. And there's there's an extra step right before we even enter our for loop. If we need to determine whether we start with addition or subtraction. So if my first I is even, then factor is going to be positive 1. Otherwise, if it's odd, factor is going to be negative 1. And that's because every other term in the summation must be a negative number. So we can declare that for every odd n, that's every other number, so every odd n is going to be negative. Also, we have to declare that 0 is an even number, just to make the math work. So with all that information, we can create a modified for loop in which each thread does a portion of the work. But collectively, they do all the work. And oh yeah, remember, we have to flip the sign of factor because every other term in the summation is a negative number. So let's put it all together. Given p threads and n terms, the ith thread is assigned to calculate the ith portion of n over p terms. That thread calculates its starting and stopping positions for its for loop. That's what all this is for. My n, my first I, and my last I. Then it calculates each term one by one, adding each term's value to the global variable of sum. Finally, the loop stops and the thread has finished its work. So, this is what the code looks like. So I would like for you to start writing this as well. I don't have an assignment out for this just yet, but expect that in the coming days, okay? The first parts of the program are the include directives, global variables, and function prototype. Following that is the main function itself. So we have the main function. It's going to have some command line arguments being passed in. This is basically the hello world program, but modified so that instead of saying hello world, we are calculating the number for pi. So this is also why I want you to write that hello world program again, because it's going to be used as a skeleton for our pi estimation program. So basically, we are creating a pointer to our thread handles, and then we are allocating memory for those thread handles. We are also... Okay, so thread count and n. N is the number of terms that are summed. Thread count is the number of threads that we're using to find the number of pi. And then sum, we're gonna use that as a global variable for calculating the value of pi. So we have 3 global variables in here. So, of those 3 global variables, 2 of them we're going to assign values using strtoll. So, thread count is going to be strtoll argv1 null 10. And then n, that's the number of terms in our sum, that's strtoll argv2 null 10. We allocate memory as we did before. So malloc thread count times size of thread malloc thread count times size of pthread t. We create threads as we did before. We say pthread create, pass in a thread handle, pass in null, pass in thread sum, and then pass in void star thread. And then we join back with the main thread, because at that point all the threads will have done their work. And then we deallocate the memory we used for those thread handles. And then before we exit the program entirely, we print out the value for pi. So we say estimated value of pi is going to be %f, and then we print out 4 times the sum. So here's that thread function. It's basically the same exact code as in here. The thread function, the thread finds terms for calculating the value of pi. So void star thread sum, void star rank. We cast that rank to be, well, my rank. We also need a factor that's going to be either positive 1 or negative 1. We'll get to that in a little bit. We need an I for the for loop. We also need to calculate my n, my first I, and my last I. Because, as I said, every thread is doing work, but we need to give it a portion of the work such that it starts at some position and ends at some other position. So we're calculating my n, which is used to calculate my first I and my last I. And that all goes in the for loop. For I equals my first I is less than my last I plus plus, and then flip the sign of factor. In that for loop, we're going to do sum plus equals. factor divided by 2 times I plus 1. And then we return null because we don't have a return value for this. Instead of returning, for example, instead of returning all the sum of all these terms, because with an infinite sum, actually, no. If we're doing a finite sum, it doesn't matter the order in which if we're doing a finite sum, which I guess this is here, then it doesn't matter the order in which we add those terms. But if you are adding terms in an infinite sum, there's this weird thing that can happen where if you change the order of the terms, you might get a different result. That only applies for certain infinite sums, by the way. So basically, we're not returning anything, rather we're just incrementing a global variable. So once this is done, when you run the program, don't forget to type in the number of terms or threads you want to use, or you'll get a seg fault. Also, because of how we coded this, be sure that the number of threads is divisible. Be sure that the number of terms is divisible by the number of threads. We don't have any code that would handle when this isn't the case, so just be careful. There is another way we can program this, but I guess I'll have to show this to you later. It's instead of doing this in blocks, we would instead have each thread leapfrog over one another so that it's a little bit more distributed, but it's guaranteed to work no matter how many, regardless of whether the amount of work was divisible by the number of threads. But again, I'll have to show you that later. Okay, so let's go back to our virtual machine here and get rid of all this weirdness here. So now we have our single-threaded pi estimation program, but we also have the multi-threaded one over here. That's the executable. I want the source code. So it's pythreads.c. Get it? Pythreads? Because pi is the Greek letter for p. Okay, anyway. This is our pi estimation program. The entirety of it. So I want you to write this for yourself. So global variables, int thread, all that. Thread function prototype, main function. We use strtool to get the number of threads and number of terms from the command line. We allocate memory for our thread handles. We call pthread create for each thread we want, and we pass it the thread sum function and the threads rank. And then after all that is done, those threads join back with the main thread. We deallocate memory that we use for our thread handles, and we print out the number that we got for pi. And this is our thread function that we are using, in which each thread is calculating a portion of that truncated infinite sum, which I guess is now a finite sum. So, we're gonna compile this program, even though I had already compiled it. It's not hello world. It's not hello world anymore. It's rather it's pythreads. So let me compile it for the sake of showing you how it's compiled. Pythreads, and then not hello world.c, but rather pythreads.c. Press enter, and it compiled. /pythreads, and I got a seg fault because I did not enter the number of threads or the number of terms. Clear? Let's try this again. I'm gonna run it with some number of threads. Let me just shrink this a little bit. I'm gonna run this with some number of threads, and if I do that, let's say I want to run this with 10 threads, and I get a segmentation fault because I did not specify the number of terms yet. Let's do that again. Let's do 100 terms. We get an estimated value of pi to be 3.13. Not good. But we get a better estimate for pi if we increase the number of terms. 3.140836, not quite right. So we can increase the number of terms again until we get a satisfactory answer. You notice how it slowed down there? So basically, we have so many terms in here that we might want to try increasing the number of threads as well. It feels about as fast, though. So that might be the limitations of this Linux virtual machine here. So, it works. Our pi estimation program is working. It might take a while for it to work, but we are getting a result. Or are we? Check this out. I ran this program several times, and I got different answers. So 3.141583, 3.14167583, 580. What's going on? So if I run this with one thread and do this multiple times, then our expected answer should be 3.141583 because it hasn't changed at all here. But if I increase the number of threads to say 100, okay, get 3.141583, but it's not guaranteed that I will get the same answer because, look, that's 141582. That's not it. And then over here, there's 141563. What's going on? Well, our program had a bug in it. And it is probably the worst bug you will ever encounter with parallel programming. Let's talk about that. So when you run this program, run it multiple times, see what happens. Run this program repeatedly with, say, 10 threads and 100,000 terms. See anything weird? Do it again with more threads. And then do it again with one thread. Sometimes, basically, what's happening is this. When we run the program, sometimes we're getting a different result. So here's why that's happening. Consider consider two threads trying to add to a shared variable. Thread 0 is trying to add 3 to the shared variable. Thread 1 is trying to add 5 to the shared variable. And the shared variable has a value of 30, so we would expect the number 38 to come out of that. However, this might not play so nicely. One thread reads the value of 30 and then computes the value of 33. But before that thread can update that shared variable, the other thread reads the value of 30 before it got updated and computes the value of 35. One thread stores the value of 33. The other thread then overwrites that and makes it 35. What should have happened is one thread adds 3 to the total to get 33, followed by the other thread adding 5 to that to get the number 38. So we were supposed to get the number 38, but it didn't work like that, so we got the number 35. We lost a term in this process. We have a race condition. It's also called race hazard. This happens when we have processes, or threads in this case, trying to access a shared variable. When you have processes or threads trying to access a shared anything, where that thing is being done is called a critical section. Race conditions happen when threads are trying to access a shared variable, but they can happen when there's shared anything. What we need is a means of keeping threads from reading the shared variable while another thread is updating it. So basically, what we need is for this to happen. Thread 0 is trying to do stuff to the shared variable, but it needs to lock out any other thread that tries to access it. Because in the regarding critical sections, we need a means of locking the critical section so no one is allowed to use that shared anything. So that way, one thread has exclusive access to that shared variable. And once it's done, it's going to unlock that shared variable so that other threads can use it. We need mutual exclusion. But that's going to be the subject of our next video. So this is going to be part 1 of 2 of getting our pi estimation program to work. So I'm gonna leave it at here for now. But basically, when we made this multi-threaded pi estimation program, we have a bug. We left in a bug. We need mutual exclusion to make sure we are not missing any values when we add these things. With that, I'm gonna stop it right here. Your next assignment is most likely going to be to write this multi-threaded, it's really gonna be 3 parts. Part 0 is where you write the brand new Hello World program, and you use that as a base for your pi estimation program. Part 1 is where you write the single-threaded pi estimation program, and part 2 is where you're gonna write the multi-threaded pi estimation program. So these instructions might come up. These instructions might be available in the next day or so, but basically, get ready to build a multi-threaded program step by step. Alright, with that, I'm gonna end it here for now. Thank you for coming along, and we'll continue this with the next video where we try to fix our race condition. Take care.